Hello everyone, I am Kiel Lozada, a fourth-year computer engineering student, and welcome to this video reflection on chip manufacturing, photolithography, and what's ahead in computer engineering. Over the next minutes, I'll walk through how chips are made, why is it so difficult, and what future trends might change the field. Also, we will lean on key source videos like chip manufacturing, how our microchips are made, why chip making is so hard, photolithography, and how CPU is made, as well as a forward-looking video on future technologies in 2025. We all know that every aspect of the modern life, from your phone to self-driving cars, relies on a tiny piece of engineered rock called the microchip. We're reflecting on four key stages of chip manufacturing and how this incredible complexity is fueling the top trends of the future. So the journey starts with the simple everyday sun where we could find the silica or silicon dioxide. First, the sun must be purified and heated to create an extremely pure monocrystalline silicon ingot, or the moon. The purity standard is astronomical, which is 1 impurity atom for every 10 million silicon atoms. Next, the silicon must be made conductive through doping, a process of introducing impurity atoms like boron be conductive or phosphorus and conductive. This controls the flow of electricity, forming the basis of every transistor. Then, the fact that the physical properties of computing are controlled at the atomic level by intentionally adding a single foreign atom, which is outstanding. It's the foundation of all digital logic. So, how do we draw circuits smaller than a virus? This is the core challenge. All fabrication happens in an environment 100 times and times cleaner than an operating room, which is called the clean room, because even a speck of dust can destroy a circuit. So, here are the critical steps. The design is transferred to the wafer via photolithography, printing with light. A light-sensitive chemical photoresist is applied via film coating. UV light is shined through a mask, the circuit's blueprint, selectively changing the chemical structure of the photoresist. Then the developer washes the exposed areas, giving a template for the next step, which is called etching. The resolution needed today requires light sources with extremely short wavelengths, and this is why the industry relies on extreme ultraviolets or lithography, a technology so complex it has a near monopoly because it is manufactured by only one company, ASML, or the Dutch multinational corporation that designs and manufactures photolithography machines. A single machine costs around $130 million. Then, according to Moore's law, the exponential growth in chip density is driven entirely by improvements in this printing process. It is a constant battle against the laws of physics. Once the layers are defined, they must be built up and connected. A single transistor is a tiny switch made up of P and N layers, an insulating layer of silicon oxide, and conductive gate. By applying a charge to the gate, the circuit switches on or off, or 0 or 1. After photolithography defines the layer, ion implantation shoots dopant atoms into the exposed silicon to specify the electrical properties of the transistors. The transistors are then linked together by layers of metal, often copper interconnects, that act as a circuit's wiring, and this creates conductors with a length of multiple kilometers on a space no longer than a fingernail. The final result is a CPU with 100 billion transistors. It's a complex, multi-layer, 2-month-long process of creation, constantly monitored by electron microscope. This immense complexity has led to massive industry specialization and consolidation, creating a global choke points. So here includes the three bottlenecks. The first one is the instruction set architecture, or ISA, the dominance of x86, Intel or AMD and ARM. Then the second is the fabrication, or the fabs. The hyper-expensive and complex manufacturing is dominated by a few giants, most notably TSMC, or the Taiwanese Semiconductor Manufacturing Company. And the third one is the equipment, the monopoly of companies like ASML for cutting-edge machines. Then this concentration of power is a source of geopolitical tension. Countries like the US, Europe, and China are spending billions in effort to secure their own chip manufacturing and reduce reliance on a single region for this foundational technology. All of the precision and power achieved in chip manufacturing is now driving the next wave of technological innovation. The complex chips we just discussed are necessary for solving problems that would take today's supercomputers millions of years. So this introduced the quantum computing. This demand for instant, intelligent responses is driving the need for processing closer to the source, powering AI-powered IoT devices and edge computing. These specialized powerful processors enable the creation of intelligent machines and interfaces, AI robotics and Gen AI, and also the virtual assistant. And ultimately, the goal is to fully integrate technology with our experiences and bodies, leading to metaverse technologies and a groundbreaking field of human augmentation, which is the examples are from the neural links like Elon Musk is doing. So the chip is not mainly the endpoint, but it is the enabler. The complexity of today's silicon directly fuels science fiction level innovation of tomorrow. So, in conclusion, we have just traveled an incredible journey from something as simple and ordinary as sand to the foundation of all modern technology, the silicon chip. It was fascinating to realize that every smartphone, computer, every car, and even satellite begins with a material we can find on any beach around the world. But through extraordinary science, precision engineering, and human ingenuity, that sand is transformed into the beating heart of our digital world. The process we explored, from purifying silicon to sculpting microscopic circuits with light to assembling billions of transistors into a single chip, represents one of humanity's greatest engineering achievements. It is a story not only of technology, but also of collaboration and persistence. Every layer, every atom, every photon of light in photolithography reflects decades of innovation and the work of countless scientists, engineers, and visionaries. Yet behind all this brilliance lies a fragile global system, a network of companies, countries, and technologies that mass manufacturing in only a few places has turned semiconductors into the oil of the digital age, shaping geopolitics, economies, and national security. The competition to lead in chip technology is not just about faster processors. It was about technological independence and control over the future. And that future is already unfolding. The chips we have learned about are enabling the next generation of innovations. Quantum computing that challenges the limits of physics, AI-powered devices that think and learn at the edge, and robotics that bring intelligence into the physical world. They are even paving the way for neural interfaces and human augmentation, technology that might one day blur the line between biology and machine. Then, when we look at this trend, quantum computing, AI robotics, edge computing, and human augmentation, one thing becomes clear. The real revolution is just in making chips smaller or faster. It is in how these chips amplify human potential. They are the invisible engines behind the technologies that define our time. Tools that extends our creativity, our intelligence, and even our humanity. So the next time you unlock your phone, stream a video, or ask an AI assistant a question, remember, it all began with a grain of sand. From that simple starting point, we have built a future that once existed only in science fiction, and we are just getting started.